Hello everyone. Welcome to second lecture of the course on reinforcement learning. I am Dhiraj Madan, and today we'll continue with our discussion about the MDP framework, and we'll also see how to compute the cumulative return of a given policy starting from a given state. Right? So first, let's okay. So this is the second lecture. And today's topic is policy evaluation. Before we move on to this, I'll just take a recap of what we have done in the past lecture. So, so what we introduced was this idea of reinforcement learning, wherein we want to learn from the feedback. How do we model this situation wherein we have to learn from the feedback? We model it via the framework of Markov decision processes. So we took an example of grid world, and we defined Markov decision process as a system which has these five sort of elements. So first is a collection of states. So a given state represents the configuration of where you are in the system, right? So it represents the possible all sort of possible combinations are contained in this state space or the set of all states, where every state is a single configuration. The actions are the possibility on which an agent can take some decision. So these actions could be, for example, in the grid world setting, you may want to move a cell up, down, left, right. So all those could be the possible actions. And then you also have something known as these rewards. So these rewards are essentially feedbacks which can be given to you from the environment. And these rewards could be positive or negative. As we have seen in the grid world example, we had both examples of positive rewards as well as negative rewards. In general, these rewards, they represent, how much is the sort of feedback you are getting. Your goal will be to take those actions which give you, in the sense, some sort of a positive reward. We'll discuss, what exactly our objective function is. But other than reward, the environment also controls our transitions in the states. So if you are in a given state and you take a particular action, what is the distribution of the next state? That is given by the transition distribution. This is also controlled by the environment. And the fifth quantity is known as the discount factor. This discount factor is, the sort of, how much is the sort of reward decaying with respect to time, right? So there is a control parameter gamma we have kept. So when we formulate our objective function, we sort of model it as a cumulative sum of sum over t, rt gamma to the power t, where rt is the reward given at time step t. And we scale it with this exponentially decaying term gamma to the power t. Right? So gamma is the discount factor, which is less than 1. So one of the reasons we have seen to introduce gamma, one of the reasons was that it models a sort of interest rate, in the sense that, like a reward tomorrow is less worth than the same reward given today. So that's what is the economic interpretation. Secondly, it also helps in upper bounding our sum. Right. And whenever we consider, and so right now we are still in the Markov decision process framework, wherein this environment is known to us. That is, we know what is the sort of reward function we have, we know what is the sort of transition distribution we have, and state space actions all are known to us. But when we'll move to the reinforcement learning setting, there we'll also look at conditions where the environment or the transition distribution or the rewards are not known to us. So in today's setting, we still know these, and the idea is that we can sort of split our system into two parts. One is the agent, which represents the sort of person who is trying to play this game, for example. So this agent has access to the current state and knows what are the possible actions which it can take. The environment, however, is controlling the sort of next state, right? So it controls, based on the action which the agent has chosen and the state which the agent is currently in. The environment controls what is the distribution over the next possible state. So this distribution, we assume that, it's there, it's some fixed distribution, and the agent is now trying to sort of maximize the rewards under the distribution. And also there is a notion of the set of rewards we have. So every state will give us a specific reward. We saw that we can also model the reward function in a different manner, wherein we consider it as a function of both state and action. In our setting, our reward is just a function of state. Now, both these rewards and the sort of transitions are governed by environment, but the agent has a choice over the actions which it can take. The choices of actions is known as the policy, right? So policy is a function. It can be a deterministic policy, in which case it's a function from the set of states to actions. So given a state, what is the action which the agent is going to pick? That's known as the policy pi. In general, this policy can also be random or stochastic, in which case there is a distribution over the set of actions given the state. In most of the algorithms, we can assume that this policy is some deterministic algorithm. For example, in the algorithm which we will see today, or not today, but maybe in the next few lectures, uh, uh, for all these sort of these value iterations, policy iterations, we will see that it's okay to assume a deterministic policy. But then many times when we are dealing with reinforcement learning setting, wherein the environment is unknown to us, over there we'll have to also model these stochastic policies, meaning that the agent can also randomly take some sort of an action which sort of leads it to some new states, right? So if an agent wants to explore the environment, we might want to take stochastic policies. Also, when we'll go to deep reinforcement learning, we'll see this policy gradient algorithm where this policy can also, where we need this policy to be stochastic so that we are able to train it. So that's roughly a summary of what we had done in the last lecture. We had also seen the notion of a trajectory. So when you start from an initial state S0 and you pick the action A0 and you move to the next state, you pick another action, move to the next state. Subsequently, whenever you move to the next state, you also obtain the corresponding reward. So all the sequence of states, rewards, actions, and so on. These form something known as trajectory. So this is essentially the entire trajectory or the evolution of how the system has evolved and what are the rewards which have been obtained. In general, we'll have to pick a policy which tries to maximize our objective. So our objective is the total cumulative payoff, where we are weighing by these exponentially decaying terms of gamma to the power. So we are trying to maximize the sum over t, rt gamma to the power t. This is what our objective is, and now we'll try to see how to maximize it. So let's move to today's lecture. Before we move on, I'll also just make one definition. So this particular expectation which we have, right? So this expectation over the policy. So this policy can be stochastic or deterministic, and the transition function S prime given AS, right? So of this quantity sum over t RT gamma to the power t. So this I'm going to define as the value function for a given policy. So this is defined as value function for a given policy pi. Okay. So this is how we define it. And note that when I say it's an expectation and consists of both pi terms and p of s prime given as terms, so essentially you should think of it in expanded terms as the expectation over. So firstly, there is the first action is chosen from A1 sampled from pi of A1 given S if it's a stochastic policy. Then essentially S1 chosen from P of S1 given A1 comma S0 and so on, right? So A2 chosen from pi of A2 given S and so on, right? So in general, AT is chosen from pi of, so this is S1. So AT is chosen from Okay, and when I'm writing this expectation, this is conditioned on S naught equals S. So essentially, A1 is chosen from pi of A1 given S naught, and similarly, AT, right? So that is chosen from pi of AT given S T minus. Okay, so first action I'm calling A naught. Okay. So A naught is chosen from pi of A naught given S naught, and S1 from pi of S1 given A naught S naught, and A2 from pi of uh, A1 from pi of A1 given S1. In general, an action AT is picked from pi of AT given ST. And the next state, ST plus 1, is chosen from the transition distribution P of ST plus 1 given AT. Right, so basically, this is just some, okay, don't get confused with all of this. But essentially, what's happening is that the way this trajectory is evolving, right? So you start from the state S naught and you obtain the reward R naught. And essentially, you sample the action. Who samples? The agent samples the action from the policy whose distribution is given as pi of A naught given S naught. Then S1 is chosen uh, by the environment, right? From the transition distribution P of S1 given A naught and S naught, and so on. So I'm just formalizing this. So essentially, AT at time step T, what's happening is that the action AT is chosen, given conditioned on ST from the by the agent with policy pi, and then the next state is chosen by the environment from the transition distribution, wherein ST plus 1 is chosen from P of ST plus 1 given ST and AT. Right. So that's all what's happening. And so basically this, okay, so don't get confused with this long chain of equations. But essentially this in summary, so what's happening over here is that there is an expectation of pi of AT given ST. So this is how AT is sampled, and ST plus 1 is sampled from P of ST plus 1 given ST. For all T. Okay. And next I have a sum over T, RT, gamma to the power T given S. So this expectation is known as the value function for a given policy pi, right? And our goal is how to actually compute this V by S. And that's what we are going to study in today's lecture. Okay. So I hope all of you get it. So let me, I don't want to bore you with too much of repetition, but essentially the main idea is that you start from a given state, you are continuously sampling the actions and the next state. So this is in the hand of agent. This is in the hand of environment. And when we are taking the actions, we are taking when we are taking this expectation, we are taking the expectation over, whenever you take an expectation, right? So it's over some distribution. So these are the distributions we are taking the expectation over, and we are only conditioning on the initial state. And when we are picking this sort of when we are having this sort of this expectation, we are considering both the distributions of agent and environment over which we are averaging out. And at every step we have this sort of this at every step we have some distribution and sampling, and this expectation needs to account for all of it. So it appears quite difficult, right? How do we actually compute this expectation, right? So there is not just one or two distributions. At every step, there is a distribution and sampling going on. And then we have this sort of this huge cumulative sum. And it's averaged over so many distribution at every time step. Like there are two distributions which are occurring for giving me reward at every time steps. And then, the next state is also conditioned on the previous state always. So that depends upon the distribution from which the previous state was sampled on, and so on. So it looks like a very complex sort of a problem now. And how do we now compute this? So the idea is that there is a very interesting dynamic programming based solution for this thing, and that's what we are going to look at now. And that's known as the Bellman equation. Okay. So let's see how to actually compute this. So when I have V pi S, So essentially, as I have just written it before, it's expectation over pi of AT given ST. And so this AT given ST is not just a single distribution, it's at every time step. So I have made that clear a few times. And ST plus 1 sampled from P of ST plus 1 given ST. And this is also at every time. And then what do I have inside this expectation? Sum over T RT gamma to the power. And then there is a condition that S naught is S. So that's what we have. So what I do is that let's look at this huge sum and let's separate out the first revolve. Okay. So this is still there. Okay. Given STAT. So let me just take out the first reward from here, which is R naught. Okay. And next what I do is that I have this T from 1 to infinity. So earlier it was 0 to infinity. Now I have from 1 to infinity. And I have RT gamma to the power T and conditioned on the fact that S naught is S. Okay. Since R naught is just R of S naught, so essentially if I just condition it, I already know that this is going to be R of S. Right? So that I can take outside this. So I can just write it as R of S naught that I take outside. Actually, I'll write this R as the cursive R, so as to avoid confusion with gamma. So this is R of S naught, and this is RT gamma to the power T. So now I have R of S naught, okay, and then there is this expectation over here. And even from this expectation, note that, since T goes from 1 to infinity, so I have R1 gamma, R2 gamma square, and so on. So I can take out this gamma term from here. So this is expectation, and as before, over both the choices of actions and the choices of fixed state. So what I do is that I take out this gamma outside, and what I'm left with is now RT gamma to the power T minus 1 given S naught equals to S. And now let's do one thing. Let's assume that this pi is deterministic. So what I'll do is that for stochastic pi, I leave it as a homework exercise for you. Okay, we'll discuss it in the next lecture. So assume pi is deterministic. The case for stochastic pi is homework exercise. So now let's look at this. So now instead of pi of AT given ST, I'll just say that AT is pi of ST. Okay. With probability 1. So AT is pi of ST. So we can have a deterministic assumption. Okay. So what I do is that now the first action I already know from here. Okay. So the first action is something which I already know because S naught is known. So I definitely know that A naught is just pi of S. So that is something I already know because I've already conditioned on S. So what I can do is that so there is this expectation which is still there. But now essentially I break this expectation into two parts. So first is that, okay, so there is A naught, which is already known to be pi of S naught. Okay. And then I am taking the expectation over S1, which comes from the distribution P of S1 given A naught and S naught. And the expectation over the remaining terms, which is from AT onwards, AT coming from pi of ST and ST plus 1 distributed as P of ST plus 1 given AT ST. So this is now for t greater than equal to 1. Okay, so for all those terms, I'm taking in separate expectation. And what I have from here is that I have sum over t, rt, gamma to the power t. Okay, and conditioned on S naught is S. And then also, I'm also conditioning on the fact that the state S1, right? So that I have already sampled here. So what I do is that I am performing this step. Okay, so first I sample S1 and then conditioned on S. So S0 is S and S1 is also being sampled over here. So S1 is S1. So I just sample S1 as well. And then I condition it in the inner expectation. Okay, so this is what we are doing. Essentially, what we are trying to use is this towering property of expectation. So this is using the towering property of expectation. So what does this say? So let us say, that you want to compute the expectation of some random variable y. Okay. Wherein the joint distribution of xy comes from p of xy. Okay. So one way is that you can first marginalize over x and then sort of compute this expectation over y. So that's one way. But then there is also another way, which is that you sort of average over all x the condition distribution of y given x, where y given x comes from p of y given x. So this property is known as the towering property of x. So what we have done over here is that, so since in this sort of expectation, so only from time step 1 is what I'm looking at. So essentially, what I can do is that I can first I can first sample S1, and instead of marginalizing over S1, what I do is that I then conditioned on S1, okay, in the inner expectation, wherein I'm computing expectation of every other quantity except A naught and S. So that's what I have done over here. Okay, so this is gamma. Okay, gamma also I had taken outside, so it's gamma, and then there is gamma to the power of t minus. So this is what we have right now. If you now look at the inner expression, right? So what is this? So this is essentially the value function, provided you start from uh, the state S1 instead of starting from the state S0. So think about it, right? Because when you condition on S0 and S1 both, then essentially this conditioning on S0 is not important, right? So why is this? Because the transition distributions only depend on the current state, right? The way these transitions happen, they only depend on the current state, not the past state. So the past states I can always remove. And if I condition on the current state, the expectation uh, just becomes the value function for this policy starting from the state S1. Essentially, what I have over here is that this is just R of S naught plus gamma and expectation of S1 sampled from P of S1 given A naught, which is pi of S naught and S naught. Of which quantity? This inner quantity. And this inner quantity is essentially nothing but V pi of S1. Because we start from the state S1, we are accumulating reward from time step 1 onwards. And the transition distributions from time step 1 onwards are the same. And the policy is also the same. So essentially, this is nothing but V pi of S1 now. Right? So essentially, V pi of S naught is R of S naught plus gamma times the expectation of S1 coming from PS1 given A naught as pi of S naught and S naught, and then V pi of S1. So we are taking the average of this quantity. And this is nothing but, this is known as Bellman's equation. And actually what we can do is that for corresponding to this Bellman equation, we can essentially write down this expectation as, for discrete sort of space, for discrete space. So what we have is expectation of S1 sampled from P S1 given A naught is pi of S naught and S naught. Okay. So, and S naught equals S, A naught is pi of S. So this is nothing but sum over, uh, this is nothing but sum over S prime or S1, P of S1 given pi of S, S and V pi of S. So overall, if we substitute the expression for expectation, what we have is V pi of S or S naught is R of S naught. Okay, actually, I have in some places I'm writing it as V pi S, some places I'm writing S naught. So let's write it S naught over here. Plus sum over S1, P of S1 given pi of S naught and S naught, pi of S. So essentially, this is my equation. And essentially, I can write down this equation for every other state. And that will essentially give me a bunch of linear equations. So we can substitute S naught as different sort of states. So how many states are there? Mod S states. Different states in the state space S to get mod S equations in mod S variables. So if you solve for it, you will get the value of V pi S for every S. Solve to get pi S for every S. Actually, if you don't want to write it in terms of S naught and S1, because then, it indicates, the start and the first state only. So you can write it in general, right? So in general for all S, V pi S is nothing but R of S plus gamma times sum over S prime, P of S prime given S and pi of S, A naught as pi of S, or A as pi of S, and V pi of S prime. So for every S, you have this particular state. Now I'm not writing in terms of S naught and S1, right? I just want to be clear that this is true for every state. Okay. So S1 indicates, that it's a specific state in the trajectory. So that's what we had when we wrote down the equation, but now we can just substitute any state. And this is true for all S. Right. So we have mod S equations, mod S variables, and you can solve for these. The question which comes up is that, does it always have a unique solution? First of all, does it even have a solution always? And if so, whether it's a unique one? Well, the answer is that yes, for gamma less than 1, okay, there is always a unique solution. The proof of that will require some little bit of basic real analysis, basic properties of convergence of sequence. So we'll do that in the next lecture. But essentially, the idea is that for, in general, it may not converge also, right? And I'll just give you, in general, the system of equations need not have a unique solution also, right? So not in general, right? Basically, let's say, not in general. Basically, if you said, for example, gamma equals to 1, you may not find a unique solution. So let me give you one example. Okay. So let's consider a simple sort of a system with two states, S0 and S1. Okay. And let me just have a single action. There is a single action A. So this is my sort of action space. This is my state space S mod S. And how do I define my transitions? So what I define is that, okay, so transitions. So first, let me also define my rewards. So let's say R of S naught is same as R of S1, which is same as 1. Okay. And how do I define my transitions now? So I define my transitions as P of, so I let me just have deterministic transitions. So P of S1 given S naught and A. Okay, so I need to define the distribution of next state given the current state given the current state is basically S naught. Okay, so S current is S naught or ST is S naught. So defining the distribution of T plus 1 and the action is just A. So this probability is 1 if ST plus 1 is S1 and 0 otherwise. So basically you will always move to S1 with probability 1 if you take action A. And similarly, P of ST plus 1 given ST is S1 and A is going to be 1 if, sorry, so this is 1 if ST plus 1 is going to be S naught and 0 otherwise. So meaning that if you start from S1, then essentially with probability 1, we are moving to S naught in the next step. And the rewards are always 1 for both. So R of S naught is 1 and R of S. Now let's write down the equation for policy evaluation. Okay, so there is actually no policy because there is only one action. So you are supposed to just pick that action. So let's have that single policy. So that policy is P of A given. Okay, so P of S equals to A for all S. Okay, so whether S is S naught or S1, you always pick the action P. Now let's write down the same Bellman equations. So what I have is that V pi of S naught is going to be R of S naught, and let's have gamma equals to 1. Okay. So we are trying to get a, we are trying to look at the case, if gamma is 1, then what happens? And my claim is that, we need not always have a unique solution. So in order to show that we need not always have a unique solution, I'm just giving one example. And if you look at this particular example, so if you substitute V pi of S naught, that will be R of S naught plus gamma times sum over S1, PS1 given, PST plus 1 given ST and AT, and V pi of ST plus 1. So how much, now the transition distribution is deterministic. So we move to S1 with probability 1. Okay. And essentially the equation just becomes this. So basically we are looking at this equation and this is a deterministic transition. So with probability 1, we are moving to S1 and we are looking at V pi of S1. So what we have is R of S naught is just 1 and gamma is also just 1. So V pi of S naught is 1 plus V pi of S1. Now similarly, if you write down the equation starting from S1, so essentially you will have R of S1, which is nothing but 1, plus gamma, which is also 1 times V pi of S naught, right? Because if you are in S1, then with probability 1, you will move to S. Okay, so essentially V pi of S naught is 1 plus V pi of S1. And V pi of S1 is nothing but 1 plus V pi of S naught. Okay. So essentially, if you now try to solve, and you will see that there is no solution. So this is just a sort of a toy example, but it shows that if your gamma is not strictly less than 1, then the system of equations need not always have a unique solution. The point was to show that. And actually, if you actually look at it, it becomes very clear also, because what's happening in the scenario is that you are starting from S0, you are getting a reward of 1, move to S1, getting a reward of 1, move back to S0, and so on. So you're juggling between S0 and S1. You're always getting a reward of 1. So your cumulative rewards, if gamma is 1, then your cumulative rewards are going to be infinite. So the solution is actually v pi s is infinite. But essentially, in terms of finite values of v, it has no solution, right? And you can check that this system of equations, it does not have a real solution, right? The only solution is if you said v pi s naught is v pi s1 is infinite. So yeah, so basically it was just like an example to show that if you set gamma equals to 1, then the system need not always have a solution. In the next lecture, we'll try to prove the fact that if gamma is less than 1, we'll have a unique solution. So in order to do that, we'll define an iterative algorithm. That iterative algorithm will also be useful for for in general for value and policy iterations later. So let's move on to that in the next lecture. So hope you liked today's lecture. Thanks a lot.